Hello all, this is Amil Naruto. Welcome to my channel. So today I'm gonna explain some of the few topics in support vector machine SVM part 2 video. So in this particular SVM series, so I'm gonna explain all the subtopics called what is mean by maximal margin hyperplane and what is mean by a support vectors. What are actually the support vectors and what is mean by a maximal margin classifier and what are all the limitation for this maximal margin classifier and what do you mean by this support vector classifier and what do you mean by these support vector machines and what are all the applications of these support vector machines. So I'm going to explain all these things, but before just deep diving into these topics, let's have a look at this amazing code from Naruto series. So growth occurs when one goes beyond one's limit, realizing that is also a part of the training. So the meaning of this code is one should push oneself. For example, if someone can run uh, for continuously for about 1 hour, let's imagine this. Uh, we should not take that for granted. I mean, we should not get satisfied for that, because if we get satisfied, then that will be the end of our success. So one should push to the core of oneself. Then only one can have successful when one can have lead. I mean, one can lead successful life. So that's the meaning of this code, and also realizing that particular thing is also a part of the training, right? So people usually don't get realized. I mean, they don't know, so they don't understand. They think themselves they had enough training, so they just usually stop. But when you compare with other person, like when you look at the other person, he's actually working more. I mean, he's actually working for more hours than us. So we don't need to. I mean, we don't need to take it for granted. So we need to push ourselves to the maximum. Then only we can be successful. So that's the meaning of this. Now let's deep dive into this topic of support vector machines. In that, now we're gonna look for maximal. What is mean by maximal margin plane, hyperplane. Okay. So now let's see this. Like okay. Now I'm gonna draw something here. Like this is our feature space. In the part 1 of this support vector machine, I have already explained what is meant by a dimensional space or what do you mean by a feature space. Okay. So if any one of you are not actually aware of this feature space, then just please have a look at this part 1 video which I have explained before. I'm just keeping the link of the part 1 video in the description of this video. So just please have a look at it. So let's move on to this topic. Like this particular x-axis and this particular y-axis is nothing but the feature space. Feature space is nothing but we are actually having, let's imagine we having the two features like x1 and this is the x2 example. Okay, and here what happens is we have few data points like this. These are my data points, and I have another category of data points. These are the category of green. Earlier was the category of blue. This was the category of the green. Okay. So, and if I want to separate these two classes, how can I do that? I'll just simply draw a single line. Okay. By this action, I can just simply divide them into the two categories. One is blue and another one is green. But in how many ways you can divide them? If I ask this question, how do you answer that? I can divide these two parts as by drawing this kind of line. I can also divide these two parts by drawing here one kind of line. I can also do that by drawing this kind of line. can also do that by sorry. I can also do that by simply like. So there are so many kind of possibilities of drawing so many hyperplanes, uh, which will actually do the same kind of job, right? Which will actually do the same kind of job. So there are so many. There are actually infinite number of possibilities of forming hyperplanes. These particular lines are nothing but the hyperplanes, right? That line is nothing but the hyperplane. So, how many hyperplanes can we draw? Can we draw? See here, there is a lot of gap between these two categories. So we can form infinite number of hyperplanes with which we can separate all these data, all these I mean these two categories. So the scope here is, what is the scope here? Scope of hyperplanes. What is the scope of drawing hyperplanes here? That is infinity. Infinite. So we can form infinite number of hyperplanes here. We can form infinite number of hyperplanes. So, but we have infinite number of hyperplanes, but we need to choose one such hyperplane, which is the best one uh, to classify this data. So how can we do that? So how can we do that actually? See here, we have two kinds of data. Like one is green, right? I'll write with this. This is the green category. Okay. And this one here, the blue category. Okay. And these are all the hyperplanes. Hyperplanes. So we have two kinds of categories, that is blue and green. We need to separate them. We need to classify them with the help of the hyperplanes. But the scope of forming hyperplanes are infinite here. Infinite. Why? Because there is there is so much gap between those two between those two categories of data. So we can draw how many. We can draw number of hyperplanes in between those two categories. So the scope is infinite here. So uh, so we need to select one best optimum hyperplane out of all these infinity. I'm just moving to the next slide here. I'll explain. See here, we need to select the optimum. We need to select the optimum hyperplane which best fits the data, fits our data. Okay, so we need one such hyperplane with which we can classify our data exactly, or in a best possible way, right? In a best possible way. Like there are so many kind of hyperplanes here and there. Okay, and there are some kind of points here. There are some kind of points here. Out of these hyperplanes, we need to choose one hyperplane. Okay. Why do we need to choose one such hyperplane? Why? Because we want to. Why? Why do we need to choose one such hyperplane? Because we are actually, what are we doing is we are actually creating, if I want to create a classifier, if I want to create a classifier, then I need to choose one such optimum hyperplane out of all those number of hyperplanes, right? So this is the reason why we are actually choosing the one such best hyperplane. And also the main reason is nothing but see here, uh, actually, for example, let's say if I have drawn one kind of hyperplane like this, okay, is it actually separating the data in the best possible way? No. Why? Because see here, most of the data points are actually lying very closer to this particular hyperplane. But here, when you see here, these data points are actually far from this hyperplane. So this is not the best possible way. Our hyperplane should satisfy both the data points, right? So then only we can call it as the best optimum hyperplane. Okay. So I'll explain. So if I want, if we want to, if we want to select one optimum hyperplane from infinite number of such hyperplanes, how do we do that? How do we do that? One such solution is nothing but maximal margin hyperplane. Maximal margin hyperplane is one of such solutions to solve this kind of scenario. Like we have so many number of hyperplanes, and we need to choose one best hyperplane out of all those infinite number of hyperplanes. How do we do that? We do that using this maximal margin hyperplane. I'll show you how to do that. And remember one thing, like this can also be called as optimal separating hyperplane. We can also call this maximal margin hyperplane as optimal separating hyperplane also. Okay, so that's it. I'll show you how does it look like. I'll show you how does a maximal margin look like. Okay. See here. Okay. So we have so many data points here, and now I have also some of the data points here also. Okay. So what happens is, for example, if I need to separate these two categories of data, I'm just drawing some kind of hyperplane here. Okay. And I need to calculate the distance between each of the data point to this particular hyperplane. Okay. For example, here I have some kind of data point, right? I need to calculate the distance, perpendicular distance between the hyperplane and this particular data point. Okay. And also I need to calculate the distance between this data point and the hyperplane. So like that, I will definitely calculate all the distances of the each of those data points and between those between the hyperplane. Okay, I'll calculate all the distances of each of those data points to the hyperplane. So like this, I'll just calculate all the data points. Okay, I'll just calculate all the data points like this between these data points to the hyperplane. And in the same way, I will also calculate the distance between the uh, the green data points and the hyperplane like this, like this, like this. So I'll calculate I'll calculate the distance of each of those data points present in both of the categories to the hyperplane. Okay. So then I can find out, I will find out the data points. Then I will find out the data points for which it has the minimum perpendicular distance to the hyperplane. That is nothing but, see here, just understand this kind of sentence here. We will, after calculating all the distances of each of those data points to the hyperplane here, we will find out the some data points for which we have the minimum perpendicular distance to the hyperplane. That's nothing but, I'll explain now. See here. See here. I'm just drawing a hyperplane to separate these data points, and I need to calculate each of the data points distance to this particular hyperplane. I need to calculate the distance between this particular hyperplane and between these data point, each of those data points. So by that, I will calculate all the distances of each of those data points to this hyperplane. Then I finally found out this particular data point here. See here, I'm just highlighting this. See here, this particular data point here and this particular data point here. Okay, and this particular data point here, okay. See here, this particular data point, these two data points in this yellow category and these two data points inside this green category are actually at the minimum perpendicular distance from this hyperplane. Okay, these are the these data points are actually lying at very closest distance to this particular hyperplane, right? So if you compare this here, see here, the distance between the hyperplane to this data point and the distance between this hyperplane to this data point are actually at the closest moment. And when you compare in this particular yellow category, the distance between this data point to this hyperplane and the distance between this data point to this hyperplane are actually at the minimum are actually at the minimum level, right? The distance between the data points to the hyperplane is minimum at these two data points instead of these two data points. When you calculate the distance between these data point and this hyperplane, see here, we will get so many, I mean, we will get so long line, right? We will get so long distance here. So this won't be suitable for this maximal margin hyperplane. Why? Because we need to select the data points which are actually lying at a very close distance to this hyperplane. So when you look at, we found some 4 points, in both, across both of those categories. Like in green category, we found two data points, and in yellow category, we found two data points which are of at the minimum distance. Then what happens? This would be our margin, right? This would be our, you can imagine here, just ignore my drawing skills, just focus on what I'm saying. This what do you say, if I need to project some kind of vertical line which is passing through these data points, two data points here, this would be my margin. And if I need to project some vertical line which is actually passing through these two green data points, then that would be my another margin. Okay, right? So this would be the margin. I can call it as margin. Okay, and this is also the margin, right? This is also the margin. And okay, we have got the word margin here now, but what is meant by the maximal? What is meant by that maximal word here? So maximal, I'll say it here. I'm writing here, if a hyperplane, has a margin, okay, let's say we have a hyperplane and we also have the margin for that hyperplane, and if that margin, okay, if that margin, that is, if hyperplane has a margin which is largest, okay, if we have a hyperplane here like this, and we also have the margins for that hyperplane, and if that margin is largest, what does that mean? If that margin is largest means, what does that mean? What does that mean? I'll say that, for example, if that margin is largest means, for example, if I have a data points like this, and for example, uh, if I found some kind of uh, let's say let's see, if I found some kind of data points here like this, okay, like this, okay, and we have some kind of data points, rest of the data points lying here, and the rest of the data points in this category are actually lying here. So what would be the margin of this hyperplane? So this will be the margin, right? Usually, in usual case, you will actually think that this would be the margin, okay, and here this would be the margin, right? The margin should pass through the data points of that closest data points of that category, okay. So you actually think that this would be the margin, so then we can call it as a maximal margin hyperplane, right? But no, that's not the case. Why? Because see here, in the definition itself, it has the maximal, okay, I'm saying, I'm writing here, maximal margin hyperplane. See here, in the definition itself, it has the word maximal. Maximal is nothing but the distance between these. I mean, what you can call uh, the distance between these hyperplane and this margin should be somewhat wider, right? if we have somewhat wider margin, then we can call it as a maximal margin hyperplane. See here, the meaning of this definition is if a hyperplane has a margin which is of the largest, right? For example, this it has the widest margin, right? Then we can call it as a maximal margin hyperplane. But when you look at here, it has the very narrow margin, right? It's very closer to each other. So this won't be considered as the maximal margin. Why? Because maximal margin hyperplane is actually a natural classifier. It will actually act as a natural classifier. What does mean by natural classifier? Natural classifier is nothing but natural classifier. I'll explain. Natural classifier is nothing but, for example, we have some kind of data points here. Okay, and I have some data points here. Okay. Okay, I have two categories. This is one category and this is another category. Let's say this is of A category, and this is of B category. Okay, and if I want to separate them, how do you do that? See here, it has a lot of gap here, right? It has a lot of gap, which is nothing but this particular gap is nothing but the natural classifier itself. Okay, here we didn't form. We didn't actually create a manual hyperplane here. Okay, we didn't actually create some kind of hyperplane here, but this particular gap is actually acting as a natural hyperplane here. Okay, this particular gap is actually separating them, the two categories, right? So we need not create any manual hyperplane here. The data itself has some kind of natural hyperplane here. So if we have this kind of natural, when I say natural, that means the gap should be wider, right? We need to have some kind of wider gap in between those two categories of the data. Then only we can have the the hyperplane, and we can have the margins so wider, right? We can form these margins so wider. Then only we can call it as a maximal margin hyperplane. Why? Because we need to find out the shortest distance between the hyperplanes and each of the data points. When we find the shortest distance, and also the margin should be wide. Okay, for example, it should not be like this. I have already earlierly I have drawn like this. See here, it should not be like this. See, we have already calculated the shortest distance between the hyperplane and the data point here. See, but the margin should be somewhat wider. Then only we can call it as a maximal margin hyperplane. Why? Because I have already given the reason. Why? Because maximal margin hyperplane is nothing but it's a natural. Okay, it's a natural hyperplane. It acts as a natural classifier. No need of forming any hyperplane manually. Okay, it actually acts as a natural classifier. Why? Because see the gap here. There is lot of gap which usually separates the two categories of the data, right? So when we can find out the smallest distance between the hyperplane and each of the data points, and that forms a vertical margin here. This forms a vertical margin here, and in between lies a hyperplane here. So this in total forms a maximal margin hyperplane. So this in total forms a maximal margin hyperplane. Okay. For example, based on the position of the data points, we can classify it to any of the class. Okay. For example, in our test data, we got some kind of new test observation in our data. In our dimension space, in our feature space, we got some kind of what we can call, we got some kind of data point here. Okay, let's say I have got some kind of data point here. So what can I how do I classify it? I'll definitely classify this data point to this particular class. Why? Because see here the position, see the position here. the position of this data point is actually lying left of this margin, right? So whenever we have a data point which is present left to this margin, left to this particular margin, then we can call that data point is belong to this particular A class. Okay. For example, if I got if I got some kind of data point here at this particular point, so how do you classify it? Do you classify this particular data point to this particular A class? No. Why? Because this is actually lying right to the margin, right? See here, we have two margins. That is left margin, right margin. Okay. Uh, so whenever a data point is actually lying left to this particular left margin, then we can consider this to that data point to this class. Okay. Whenever a data point is actually lying right to this margin, then we can consider this data point which is belonging to this particular B class. Okay. So based on based on this process, we usually classify any of the data points using maximal margin hyperplane. Okay, so if we have already classified, right? We have already classified a data point based on this approach. For example, if it is lying actually left to the margin, then we classify to this to this category A, and if it is lying actually right to the right to the margin, then we usually classify this data point to this particular class B. Then this total process is nothing but we have already classified, right? So we have classified using this maximal margin hyperplane. So this process is nothing but maximal margin classifier, right? Why? Because here we are using this maximal margin hyperplane. That's nothing but this particular. Okay, this is the maximal margin hyperplane, right? Using this maximal margin hyperplane, we have categorized these data points which is belonging to this class, and this data point which is belonging to this class, right? So this whole process is nothing but maximal margin classifier. Okay. So I'll tell you one kind of scenario here, which may usually face a lot more times in the industry. It's nothing but what we can do is, for example, we have this feature space, right? X1, X2, okay, and we have some this hyperplane, and we have some kind of data points. We have some kind of data points like this, okay. And when you calculate, if you calculate the distance between those these of them, then we can find out this particular data point has the minimum distance, perpendicular distance. See here, this is the minimum perpendicular distance, right? And also this particular data point has minimum perpendicular distance, okay, in this particular class. So these data points will usually form a margin, okay. And when you consider here, these data point and this data point are actually lying very at the minimum perpendicular distance. So we calculated this we found out that this has the minimum perpendicular distance, and we found out that this has the minimum perpendicular distance. So what can we do here? We can form a margin across which is passing through these points, okay. So this will be our margin, okay, in general case, okay, usually. And here we have one kind of scenario, like we usually assumes usually assumes our classifier will have a large margin on train data and also on the test data. Okay, we usually feel this margin will be wider. That is nothing but this margin will be larger. Okay, larger in size, both on the train data, and both on the test data also. We usually think like this, but we may face some kind of situation in which our classifier has we may face like okay, I'm moving to the one minute. Okay, so we may face a I'm writing. We may face some cases where our classifier has large margin on train data but very small margin on the test data. Okay, so what does this mean? See here, what I'm trying to say is we usually think this margin would be wider. Okay, this margin would be so wide for both the train data and both the test data. Okay, we usually think like this, but we may face some kind of situations where our classifier has large margin only on the train data. Okay, we only have such large margin on the train data, but we don't have any kind of large margin on the test data. We may find some kind of a small margin for this test data. Then what happens? Okay, then what happens? This may lead to that overfitting, right? This may lead to overfitting. Why? Because I have large margin on the training data. That means it's actually the accuracy will be definitely good. Why? Because see here, the margin, whenever the margin is higher, then that means with so much confidence interval, we can surely say that this particular any of the data point is actually belonging to this particular class, and any of the data point is actually belonging to this particular class. Why? Because the margin is very large. I'll explain that topic later. But now, see here, when we usually think like our classifier will have large margin for train data and also for the test data. Okay, so we usually think like this. We usually think that our classifier will have large margin on the training data and on the test data, but we may face some kind of cases here. Our classifier will have large margin only on the training data, but not on the test data. Okay, we can find small margin on this test data. These situations may lead to overfitting. And why does this lead to overfitting? I mean, why does such scenario will actually occur? Why? Because actually this second point, right? This second point, this occurs. This occurs when we have large number of columns. Okay. For example, when we have so many number of columns here, then we can face some kind such kind of situation here, right? Where our margin will be very large for train data, but it will be very small for our test data. This situation may arise due to when we have a large number of columns. Okay, this is the situation. And I have already shown you. When we have when we have some kind of new test data here, how do you classify them? Actually, it is actually lying left to the margin plane, so it belongs to this category. When I say I have some kind of test data here, how do you classify them? It is actually lying right to this marginal plane, right to this margin, so it is actually belonging to this particular category. This is theoretical approach, but mathematically, how can you explain this concept? I'll explain. I'll show you mathematically how you can explain such topic. Okay, so how does the maximal margin classifies? Okay, for example, you know the equation, this equation, right? F of x star is equal to beta naught plus beta 1 plus beta 2 x2 plus and so on plus beta p xp. So this would be our equation, right? I mean, these are all the parameters. This is the intercept, and these are all the slope. Beta 1, beta 2, beta 3, and so on. Beta p are all the slopes. And x1, x2, x3, xp. These are all our features, nothing but the columns. And f of x is nothing but our model, right? This entire equation is nothing but a representation of our model. Okay. So when you compute this kind of equation, and if you got, okay, if you get f of x, if you get f of x is greater than 0, then you can say that, let's say we have a two classes. Okay, for example, okay, let's say we have two classes, that is apple and the next one is banana. Okay, so let's imagine like this. So what happens if f of x is greater than 0? I can say that x belongs to banana. Okay, and if f of x is less than 0, then what happens? I can definitely say that x belongs to the other category. Other category is nothing but, what is that other category? X belongs to the apple. Okay, x belongs to this apple category. So this would be the scenario. Nothing but this is a kind of mathematical approach where we can explain this concept, the classification of any data point. Here, this is a theoretical concept, and when you want to know this particular concept in a mathematical way, this is the mathematical approach. We usually calculate the f of x. That's nothing but the representation of a model. And when after computing this f of x, if your f of x is greater than 0, what is meant by here the greater than 0? What is meant by greater than 0? Greater than 0 is nothing but the positive, right? If any number is greater than 0, that we can call it as a positive number. Okay, if our number is positive, we can assign this particular data point to a particular class, no matter whatever it is. For example, I can also assign this x belongs to apple here, but since I have assigned this x belongs to banana, so I am taking this situation as x belongs to apple. Okay, no matter, you can also consider vice versa also. Okay, so, and what happens if f of x is less than 0? That means, if what happens when a number is less than 0, what is less than 0? Less than 0 means -1, -2, and so on, right? So that is nothing but the minus, negative. So this is the negative number, right? So this would be the scenario mathematically. So, and now let's move on to the next set. And okay, so here, okay, I got some kind of data points here. Okay, so and also have some kind of data points here. Okay, so I need to divide them. How do I need to divide? See here, I can, here itself, here it has some kind of huge gap, right? So here it naturally has some kind of hyperplane, which is nothing but the maximal margin hyperplane. It usually acts as a natural classifier also. See, when you calculate the each of the perpendicular distance between the hyperplane and the data point, see here, what are the data points which has the least perpendicular distance? Perpendicular distance means this distance. Okay, this distance. Perpendicular distance means the distance between the hyperplane and the data point. So, which are the data points which have, what are the data points which have the least perpendicular distance? So I found out that this is one such data point which has the least least minimum distance, minimum perpendicular distance. So this is the data point. Okay, and this is also a kind of data point which is having the same minimum distance, and this is also the data point which is having some minimum distance. Okay, and when you look at here, this data point is actually in this category, in the category of this red data points. This data point is actually having the minimum distance, and when you look at here, this data point is also having the minimum distance. Okay, when you look at here, this data point is also having the minimum distance. So if I want to consider a what do you call, a margin here, so how can I draw that? See here, I can usually draw like this. So this would be my margin, and here in this side, this would be my margin. Okay, so this would be my margin. And what do you mean by the support vectors? Okay, what do you mean by the support vectors? So uh, I can call some kind of data points as a support vectors. Those are nothing but this data point, this one, this one, this one, this one, this one. Okay, right? These six data points. These six data points are support vectors. These six data points are nothing but the support vectors. Why support vectors? Why? Because, for example, if you can change this particular data point's position, okay, then the whole hyperplane angle will be changed, right? How does that happen? I'll explain. See here. See here, I have a hyperplane. Oh, sorry, I don't draw this hyperplane right now. I will usually draw some kind of data points. See, I have some kind of data points here, but earlier I have this kind of data point here, but now I have purposefully changed this particular data point's position to, let's say, this particular data point, right? I have changed this data point uh, here, and these two. Okay, I'll show you. For example, I have these three data points, right? See here, I'm placing the three data points. 1, 2, 3, right? But instead of placing this data point here, I'm purposefully changing this location of this data point here. See here, instead of placing this data point here on the same line, I'm actually intentionally changing this data point to this location. And I want to see what happens. Does that actually change my angle of the hyperplane or not? I just want to see. Okay, what happens? Let's see. And I have some red data points, right? See here, I have some red data points like this. I have some red data points, but here these three data points I have. Okay, see here, this particular data, this particular data point, this data point, and this data point. Earlier, I used to have these three data points on a same line. Okay, on a single line. But now intentionally, I want to change the location of this particular data point. Okay, so what happens? See here. Where is my eraser? So I'm just actually changing the location of the data point of this. Instead of placing this data point here, I want to place this data point here. Okay. Then what happens? Then what happens? Then what will be my margin here? See here. Then the hyperplane will be like this. The hyperplane will be like this. Okay. And the shortest distance would be this one. And the shortest distance between the hyperplane and the data point in this category would be this one. See here, earlier my hyperplane would be in this position, but now it has changed to somewhat in some other location, right? Earlier I used to have the hyperplane in this direction with a wider margin here and here, but now after mislocating, after just disturbing the location of those data points, then I am actually getting a hyperplane which is of a different angle. Okay, so this is happening due to the fact that these data points are our support vectors. Support vectors is nothing but, see here the word support. Support means these data points are actually supporting this hyperplane. Okay, for example, these data points are actually moving. These data points are actually what you can, for example, these data points are actually bearing the weight of this hyperplane. Okay, bearing the weight of this hyperplane. And here these data points are also bearing the weight of this hyperplane. So these 6 data points combining, I mean, by combining these six data points are actually bearing the weight of this hyperplane. So that's the reason for which the hyperplane is actually in a standard position, right? If I want to change one of the 6 points position, then what happens? The angle of this hyperplane will also be changed. Why? Because that's the relation. I mean, the location of these support vectors is directly proportional to this location of this hyperplane. If I change any of these data points location, then automatically my hyperplane will be changed. So that's the reason why we are actually calling these 6 data points as the support vectors. And how do you identify what are my support vectors? That's nothing but the data points which are actually placing at the closest, I mean, at the minimal distance from the hyperplane. See here, this data point is actually having the minimal distance, right? And this data point is also actually having minimal distance. It is also having minimal distance, and the same applies here. These 3 data points are also having the minimal distance. So that's why these 6 data points are actually considered as the support vectors. And if I, for example, if I want to see here, did you observe this particular data point here lying outside, I mean lying here at this particular position? So what I want to say is I want to change this particular location of this data point. See here, I need to change. See here, I am changing the location of this particular position. For example, I want to place this particular data point here. Okay, instead of placing this data point in this particular earlier location, I want to place the data point here. Then what happens? Does this data point location impacting my hyperplane? No. Why? Because these are actually see here, these remaining data points. Okay, the rest of these remaining data points are actually not gonna impact our hyperplane's location. Only the data points which are our support vectors will be going, I mean, will be going to impact our hyperplane. See here, the same is the case with this particular class also. The rest of the data points here will not be impacting our location of the hyperplane. Only the data points which are nothing but the support vectors will actually impact the location of the hyperplane. So by observing the entire scenario, what can you decide? I can just simply decide. And I can give one kind of a kind of conclusion here. Conclusion is nothing but the hyperplane will actually depend on, it will depend on support vectors. The hyperplane will actually depend on the support vectors. That's nothing but this particular location of this hyperplane will actually depends upon the location of the support vectors. If any of those six if any of those 6 data points, if I change any of those 6 data points, then definitely it will impact the location of this hyperplane. Okay, but if I change any of these remaining data points, it will have no impact on this data plane in this hyperplane, right? So this would be an important scenario which you will need to be keep that in mind. So let's move on to the next slide here. Now I'm gonna explain how to construct. I want to explain how to construct a maximal margin hyperplane. Not hyperplane actually, it's a classifier. How to construct a maximal margin classifier. How can we do that? See, I explain. Let's say we have uh, say we have n number of training observations. For example, how to construct the maximal margin classifier. So for this, I'll explain with the help of some kind of expressions and with some kind of notations. So let's say we have n training observations. Okay. So these are all the n number of data points. Okay. N training observations. Okay. So observations are nothing but the you all know very well that's x1, x2, x3, and so on, xn. So these are all the observations, and such observations we have n number of training observations we have. Okay. So, and we also have the class labels, that is y, sorry, y1, y2, and so on, comma, yn. These are all the class labels. So these are all the class labels which are of usually only two categorical. Like these belongs to whatever maybe the categories is. They usually belong to these two type of categories. That is -1, comma 1. So our categories, so we have the class labels either of that belong to -1 or either it belongs to +1. Okay. So we have a number of training observations, and we have few class labels. Now based on these two criteria, we need to construct the maximal margin classifier. Okay. So how to do that? Let's have a look at here. I'm just going to the next slide. So here okay, so we are actually constructing the maximal margin classifier. Okay. we are actually constructing maximal margin classifier based on, with the help of these n number of training observations and so many class labels which belongs to either -1 or one category. Okay, so based on those criteria, we are actually gonna construct a maximal margin classifier. So how to do that? Let's have a look here. So we have a specific kind of problem here. That is, our goal is to maximize. Our goal is to maximize m. That's nothing but beta naught, beta 1, beta 2, and so on, comma, beta p. Okay, and this implies to sigma j equal to 1 to p into beta j square. Okay, beta j square is equal to 1. Don't worry, don't bother about all these jargon. I'll explain each one of those. Each of those expressions I'll explain. Don't worry, just observe carefully. And also we have the expression yi of beta naught plus beta 1 plus beta 2 beta naught plus beta 1 x1 plus beta 2 x2 plus and so on plus beta p xp. It should be greater than or equal to capital M. Okay, so this will be the this is known as the optimization problem. Okay, so this is nothing but the optimization problem. Here, if we want to construct a maximal margin classifier, here we need to maximize this particular value, that is m, and here we have the parameters beta 1, beta 2, beta 2, and so on, beta p, where we have the standard expression, that is beta j square is equal to 1. I'll explain, don't worry. But here just observe this equation, yi of beta naught plus beta 1 x plus beta 2 x2 plus and so on plus beta p xp is greater than, yeah, this should be greater than capital M. Okay, so here this is known as the optimization problem. This is known as the optimization problem. Okay, so I'll explain each one of those, don't worry. So here what is he saying? This entire expression should be greater than or equal to 1. So what does that mean? So he is actually saying, like, if capital M is positive, then each data point will be placed on correct side of hyperplane. So the meaning of this expression is, the meaning of this maximize m, or the meaning of this particular equation, that is the entire expression should be greater than, the value of this entire expression should be greater than m, is nothing but if this m is positive, if m is positive, then our data point will be placed on the correct side of the hyperplane, right? Correct side of the hyperplane. That's nothing but indirectly what does this mean is, here the meaning of that is, this particular expression is yi of beta naught plus beta 1 x1 plus yi of beta naught plus beta 1 x1 plus and so on plus beta p xp, it should be greater than 0. So the meaning of this particular statement, that is, if m is positive, then each data point will be placed on the correct side of the hyperplane. M is positive means this entire equation should be greater than 0. Then only we can definitely say that the data point will be correctly placed. I mean, this data point has actually been correctly placed on the correct side of the hyperplane. We can say that. Okay, I'll explain with the help of an example. Don't worry. So this will be the meaning of this particular statement. And I have another one here. For example, if beta naught plus beta 1 x1 plus and so on plus beta p xp is equal to 0, then we can say that this equation is defining a hyperplane. That means, see here, this equation, if this entire expression is greater than 0, then we can definitely say that each data point will be definitely correctly placed on the correct side of the hyperplane. Okay. If this entire expression, is equal to 0, means this equation is actually defining a hyperplane. Okay. And then if k of beta naught plus beta 1 x1 plus and so on plus beta p xp is equal to 0. Why? Because here I have said that only this particular expression, that is beta naught plus beta 1 x1 plus beta p xp, these are all the parameters combined with our features x1 x2 and so on xp. If this entire expression is 0, but here if this is 0, then it actually implies that k of beta naught plus beta 1 x1 plus beta p xp is also 0, where k is not equal to 0. Okay, where k is not equal to 0. So I'm just moving to the next slide here. I'll explain, don't worry, don't get confused. I'll explain after writing all these equations. I'll explain one of each of those expressions. So what we can say with this particular constraint, the perpendicular distance from hyperplane plane to ith observation is yi of beta naught plus beta 1 x1 plus and so on plus beta p xp. We can write this. Why? Because see here, if we have this mathematical space or the feature space, here we have the hyperplane, and here we have some kind of data points here, and here we have some other kind of data points here. See here, this equation is nothing but it's the perpendicular distance from the hyperplane to the ith observation. For example, if this is the data point, okay, the distance between the data point and this particular hyperplane, distance between the data point and hyperplane, distance between the data point and hyperplane. See here, all the distances between the data point and the hyperplane is nothing but we can represent this particular distance mathematically as yi of beta naught plus beta 1 x1 plus and so on plus beta p xp. So here I have said the constraint, this particular constraint, right? So what is mean by the constraint here? Actually, see here, I'll explain. So the constraints nothing but sigma j is equal to 1 to p beta j square is equal to 1 yi of beta naught plus beta 1 plus and so on plus beta p xp should be greater than or equal to m. So these are the constraints here, right? With this particular constraint, we can say that our equation is nothing but a representation of the distance between the hyperplane and the each of the data point, right? So this particular equation here, see here, this particular equation, this equation makes sure that each data point is on correct side of hyperplane, at least at distance m away from the hyperplane. So just observe this statement here. This particular equation, that is yi of beta naught plus beta 1 plus and so on plus beta p xp should be greater than or equal to capital M. So here what we are actually saying is this equation makes sure each of our data point is on the correct side of the hyperplane. That is, if we have calculated this entire expression yi of beta naught plus beta 1 and so on plus beta p xp, and if that value is greater than or equal to m, okay, if that value is greater than or equal to m, then we can confidently say that each of our data point is actually on the correct side of the hyperplane. And also, what is mean by this particular m? M is nothing but at least a distance m from the margin. So when you want see here, look at here. So m is nothing but this particular distance, right? For example, the distance between this data point here and to this hyperplane, this is nothing but the distance m. So what is meant by m? M is nothing but the margin here. See here, by this we can find out some kind of margin here, right? I'll explain right here. See here, we have got a hyperplane and for which we have the margin here, right? So this particular margin is nothing but the distance m. Okay. For example, we have the equation y of beta naught plus beta 1 x1 plus beta 2 x2 plus and so on plus beta p xp. If it is greater than or equal to m, then we can say our data point is lying is lying on correct side. Is lying on correct side of uh, the hyperplane with the distance m. Okay, with the distance m. Okay, for example, I have calculated the distance between this particular data point and to this particular hyperplane is, for example, let's say I have calculated the m is equal to I have calculated the distance I have got is equal to, for example, 20. Let's imagine I have got the distance between this data point and the hyperplane as 20. So what can we say? For example, if we have calculated the entire equation and which is greater than the m, that is nothing but for example, we have got this entire equation value as, let's say, some 40, okay, which is greater than or equal to 20, right? 40 is greater than or equal to 20. Then we can say our data points are actually, what is mean by this particular greater than? Greater than is nothing but, see here, we have got the distance 20, okay, 20, and here uh, we have got the equation that is 40, right? So 40 is greater than or equal to 20. So what is the meaning of this particular expression, greater than or equal to 20? That means our data points should not cross this particular margin. Why? Because if our data point has crossed this particular margin, we can't, we can't say with the amount of confidence, we can't say with confidence that this data point is belong to this particular region, right? For example, our data point has crossed this particular margin. My new data point has been placed here, okay? Then can I say that this data point is actually belonging to this particular class? No, I can't even say. Why? Because see here, the data point is actual. Here we have the margin, right? So the data point should be placed outside of the margin. That's why we have placed greater than or equal to symbol. That means m is nothing but the distance here, okay? So our calculation part, our model, that is 40, should be greater than of the m, right? Greater than of m means that particular data point will definitely lies here or here, whatever may be the location, but it definitely will lies outside of the margin. Then we can confidently say that data point is actually belonging to this particular region. For example, I have the data point here, okay, I have a new data point here. Then can I say this data point is actually belonging to this particular region? Yes, I can say. Why? Because this data point is actually away from this margin. If this particular data point is actually present in here, I can't even say with amount of confidence. Why? Because i can't i mean I can't give assurance that this data point is actually belong to this particular. Why? Because here I have the margin, so it should not cross the margin. That's what the meaning of this particular equation. Here the greater than or is equal to is nothing but the value of this particular expression should be greater than this margin, right? M is nothing but the margin here. So overall, what did you understand? So, but I have understood one thing, like this particular problem. So here we can consider that m is nothing but the margin here. So m is nothing but the margin here. Okay, we need to maximize this particular margin. Why? Why? Because see here, what did I say? See here, I have said maximize capital M. Maximize means we need to see. For example, it is the hyperplane. Okay, it is the margin here. Our goal is to maximize this particular margin. Our goal is to maximize this particular margin. Why? Because the wider the margin, then the confidence will be high. For example, if we have some kind of narrow, okay, if for example my data point is actually very close to this particular margin, then can I say that it belongs to this particular category? For example, I have some kind of data points here. So can I say that this data point is actually belonging to this particular category? No. Why? Because it's actually very close to this margin. So our goal is to wide this margin, right? Our goal is to maximize this margin. so that we can gain some amount of confidence. With that confidence, we can definitely say that this data point is actually belonging to this particular class, or whether this data point is actually belonging to this particular class. Okay, that's the meaning of this. So by the overall scenario, what we have done is we have understood that S is M is nothing but the margin. M is nothing but the margin, and also to solve this, to solve the above optimization problem, to solve the above optimization problem, we need these parameters, right? And so on, these parameters. Okay, we need parameters beta naught, beta 1, and so on, beta p. Okay, we need these parameters. Why do we need these parameters? To maximize, right? To maximize capital M. Okay, so our goal is to solve this particular, our goal is, see here, I'll explain. See here, yeah, this is known as the optimization problem. What is this optimization problem? This, see here, I have already said our goal is to maximize the capital M. Capital M is nothing but the margin. Okay, for that we need these parameters. Okay, forget about these parameters for now. Just look at here. These are all the parameters, right? Bj square is nothing but the parameters. Why? Because see here, beta naught plus beta 1, beta 2, and so on, and so on. So in short, I have just represented as beta j square. Okay, so here our expression, that is yi of beta naught plus beta 1 plus beta 1 x1 plus beta 2 x2 plus and so on, this is nothing but our model, representation of our model. It should be greater than this margin M. Okay, why? Because if this is greater than M, that is if this is positive, if M is positive, then we can say our each data point will be correctly placed on the correct side of the hyperplane. That is, there has been, I mean, we can proudly say that no data point has been misplaced or misclassified. Okay, if M is positive. Okay, if M is negative, then we can't say, we can't be sure that there may be some kind of misclassification also happened. We don't know. Okay, that is nothing but the mean. What is the meaning of this M is positive means? The meaning is this entire expression should be greater than 0. Then only M will be positive. If it is entire expression will be less than 0, then M will not be positive. It should be negative. Okay. If this entire expression is equal to 0, then what happens? It's nothing but the data point is actually lying on the hyperplane. Okay. See here. If we found this kind of situation, what happens? Then we can't say with confidence that we can't be sure that this data point is actually belonging to whether this class or whether that class. We can't be sure. Why? Because these data points are actually lying on the hyperplane. So this situation occurs when this entire expression is equal to 0, right? So that's what it is. See what I have explained. So this entire expression, with the help of these constraints, okay, constraints means here nothing but the parameters here, right? Constraints is nothing but the parameters. See here, with the help of these constraints, we can find out the perpendicular distance from hyperplane to ith observation, right? This particular distance, right? This particular distance between the data point to the hyperplane, we can write as this particular equation, yi of this. So our main entire conclusion is nothing but, the entire conclusion is yi of this expression should be greater than or equal to M. Okay, this equation makes sure this each data point is placed on correct side of the hyperplane. That is, no misclassification has happened. Each and every data point has been placed correctly. there has been no misclassification at all. Okay, we can proudly say. Why? Because it is actually greater than the margin. Okay. M is nothing but the margin, we have already known. So with the help of this equation, we can say our data point is actually lying on the correct side of the hyperplane with a distance m. Okay, with a distance m. M, what is mean by m? M is nothing but the distance between the data point and the hyperplane, right? So that's nothing but the margin. Nothing but the margin. So here, that's what it is. And now I'll explain what are the exceptions. Some exceptional case. We have some kind of exceptional case. For example, see here. Okay. For example, right now I'm explaining when do we use this maximal margin classifier and when we should not use this maximal margin classifier. Now I'm going to explain. See here, for example, look at here. We have the two kind of classes. That one class is the blue, another class is the green. Okay, let's say blue, green. So I want to separate these two classes. Can I separate? Yes. How? I need not create any kind of hyperplane here. Why? Because this data itself is having some kind of gap in between them, right? This particular gap, see here, this particular gap is itself acting as a natural classifier. Okay, is the gap here itself acting as a natural classifier with which we can divide the two separate classes. Okay, as these categories belong to blue and these data points are actually belong to green. With the help of this natural separating hyperplane, we can classify that. So in this scenario, we can apply maximal margin classifier. Why? Because there itself it has a natural hyperplane. Okay, with the help of this natural hyperplane, we can extend. We can use maximal margin classifier. So that particular natural hyperplane is nothing but the maximal margin hyperplane, right? See here, this particular this natural hyperplane is nothing but maximal margin hyperplane. But what happens is, but in most of the situations, we don't even find these kind of situations. That's what I'm saying. See here, I'll explain. For example, I have a scenario like I have a scenario like this. In this scenario, can we apply this maximal margin classifier? Okay, just like if I want to draw some kind of line like this, can am I able to separate both the classes correctly? No. Why? Why? Because see here, the right of this, the right side of this hyperplane has two categories, green and blue lying. The both categories have been mixed, right? The same has happened to the left side of the hyperplane also. See here at the left side, the both categories are actually in one single side. So this is not a correct classification. This will be a wrong classification. This will be a blunder. Okay. Why? Because see here, the scenario here is non-linear. For example, if I have some kind of group like this and some kind of group like this, if I want to separate, I can draw a simple hyperplane like this. But what if I have a scenario like this? Can I draw? No, I can't draw like this, because with which I can't even separate the two classes. So this is a kind of linear. This is a kind of linear scenario. Okay. But this here, it's a non-linear scenario. It's a non-linear scenario. So in such cases, we can't apply this maximal margin classifier here, right? We can't apply for such cases. So if we can't apply this maximal margin classifier in such cases here, so what are all the options we can solve this particular question? How do we solve them? So what we can do is we just simply we use we use the concept of the same separating hyperplane. Separating hyperplane to create a hyperplane which almost classifies observations perfectly using a soft margin. Okay, remember this word soft margin. It is very, very useful in the interview point of view also. So just remember this particular word, soft margin. Okay. So how can we do such kind of things with the help of this soft margin? How do we separate? See here, we have a non-linear scenario, and we need to separate the we need to separate the classes here, just like this. See here, we have a non-linear scenario here. We need to separate those data points, but we can't even use this maximal margin classifier here. Why? Because this maximal margin classifier is only applicable for the linear kind of scenarios like this. Okay, but for the non-linear kind of scenarios like this, we can't even apply maximal margin classifier. So how to solve them? We use the concept, a similar concept of the separating hyperplane to create a new hyperplane which almost classifies the observations perfectly. That's nothing but let's say it 90% it classifies the observations 90% correctly, but some 10% it may misclassify. Okay, so I'll explain this entire concept. So this entire concept has a kind of name. That name is nothing but support vector classifier. Support vector classifier. Okay, so this entire process has a name. Using a soft margin, we usually do this kind of process. That is, our classifier will classify the objects correctly with 90%, and it allows some kind of misconception with 10%. See here, this 90-10 is nothing but just for the example purpose. This is not the exact scenario. our main exact agenda is we correctly classifies, okay? We correctly classifies most times, okay? Most of the times. But some observations can be misclassified. I'll explain with the help of an example here. Just remember this word soft margin. So it has a deep meaning. Okay, it has a deep meaning. Soft margin is nothing but so it has a very kind of deep meaning. I'll explain what it is meant by. But just look at here. This entire process is nothing but the support vector classifier. So what is the support vector classifier? It's nothing but it's the generalized form of maximal marginal maximal margin classifier. Okay, so support vector classifier is nothing but it is the generalized form of the maximal margin classifier. So earlier, with the help of the maximal classifier, we can only solve the linear kind of scenarios, but we are actually extending this particular approach to the non-linear scenarios also. So we have a particular name for that. That's nothing but the support vector classifiers. So I'll explain with the help of an example so that you can understand better. Okay. But before that, I'll explain. I just want to give you an example. Uh, okay, I just want to give you an example for why. Okay, why can't we use maximal margin hyperplane for non-linear scenarios? I'm gonna explain this particular topic with the scenario with the help of an example. Okay, I'm gonna give you an example. For example, let's look at here. See, it has some kind of data points here. It also has some kind of data points. See here, our data points which belong to the both the categories. That is, in this whole data, the data has been involved from the two categories, right? One is blue, another one is green. So we have the data points from both of these categories. But here, both the data points have been mixed. So can we use this maximal margin hyperplane here? No. Why? Because we can't even apply here. Because a hyperplane is nothing but it's a linear kind of thing, right? When we apply this linear kind of hyperplane here, is it actually dividing the data correctly? No. Is it actually classifying the data points correctly? No. Why? Because the data have been mixed. So we can't even apply the maximal margin hyperplane here. So For example, for example, let's say we have a data. Let's say we have a data and the data is well separated. Okay. The data is well separated, like the earlier form of data. Okay. Now we need to divide this particular data. How do we do that? We have a natural hyperplane, which is nothing but the gap itself. This gap itself is acting as a natural classifier here. This is nothing but the maximal margin hyperplane. Everybody knows that. So what happens is, even we have this particular natural classifier, we can't classify these two data points perfectly. Why? Because let's say I have some kind of a new data point. Okay, a new data point. Let's say I have some kind of a new data point like this. Okay, like this. Then what happens? The hyperplane will definitely have some experience some kind of a huge drastic change. How that has happened? I'll explain. See, for example, if one additional data point has been placed here, then what happens? I may draw this particular hyperplane as like this, right? See here, the entire structure of the hyperplane has been changed. Okay, let's say if I just place this particular data point as let's say if I have placed this entire data point as like this, what happens? We can also separate this particular data as like this also. Okay, see, by this what is actually happening is, earlier we have the two categories and we have one single hyperplane, and the gap between the each data point to this hyperplane is actually very far. Okay, so we have the enough wide margins. Okay, we have such wide margins here. Okay, we have such wide margins, but here in this case, what is happening here? Here the margin itself is actually decreasing. See here, the margin itself is actually decreasing. Then what happens? We can't even confidently say if margin size decreases, then we can't confidently say that a data point is belonged to a particular class. If we want to clearly, or if we want to perfectly classify a data point, this data point should have some kind of a minimal, what we get, basic distance between this hyperplane and that particular data point. See here, if we consider this particular hyperplane, the distance between these data points and this hyperplane is very, very short. So we can form very minimal margins like this. Okay, so we can have the very minimal margins like this. So what is this particular with this particular short type of margins, we can't even clearly classify. Why? Because this particular data point is actually very, very close to the margin. So if any data point is actually close to the margin, then we can't even say that this particular data point is actually belongs to this particular class or this particular class. We can't even say. And also, for example, if we have this particular maximal margin, and we have got this kind of margin here, okay, and here we have some kind of data points here, right? Oh, sorry. We have some kind of data points here. We have the rest of the data here, and we have the rest of the data here. Okay, so we have like this, and this particular hyperplane is nothing but the maximal margin hyperplane. Okay, and this maximal margin hyperplane is nothing but it's a very sensitive. It's a very sensitive to the single data point. Okay, single data point. For example, here, instead of placing this data point here, if I place this data point like this, sorry, not like that. If I place this data point like this, then definitely the margin size will definitely be reduced. Why? Because see here, what is the minimal distance between the hyperplane and the data point? Earlier, this was the data point which is actually here. So this was the minimal distance, right? But now the data point has been come forward, so this would be the maximal distance. I mean margin. This would be my margin. Okay, this would be my margin. So what happens? A change in the data point is actually changing the structure of the hyperplane. So this maximal margin is sensitive. We need to say this maximal margin is sensitive to change in a single data point. To change in a single data point. So that's nothing but okay, no matter. I mean, for example, if I change like this, let's say, okay, if I am changing this particular data point, instead of placing this particular data point here, I am placing the data point as here. Okay, then there will be no change. Why? Because this hyperplane will only be depending on these support vectors, right? Support vectors are those which are exactly lying on the margin, right? If any data points are actually lying on the margin, then those are nothing but the support vectors. So if any support vector is changed, then definitely it will impact on the angle of the hyperplane. Then that will definitely impact on the structure of the hyperplane, right? Did you get my point? So what I'm saying is, see here, I have got some kind of data points, let's say 4 or 5 data points on exactly on the margin, right? Exactly on the margin here. But there are some other data points which are away from the margins. So if we change any of these external data points, then there will be no impact on this hyperplane. Okay, if I change any of these remaining data points, then there will be no change in this entire hyperplane. But if we change any of these data points which are exactly lying on the margin, then definitely there will be some kind of change inside this structure of the hyperplane. For example, if I changed like this, okay, if I changed right, I have remained these entire 4 points as it is. Okay, but this particular first point I have just moved it to the, I have just pushed it to the forward. Okay, then our hyperplane will be, then our margin will be like this. Then here our margin will be like this. Then our hyperplane will be like this. See here, earlier our hyperplane will actually lying in between these two. But what happens if it just moves forward, then the position of this hyperplane will be changing. So here the maximal margin hyperplane is actually depending upon the support vectors here, right? So this property, if we change location of one data point, sorry, not one data point, one support vector, then location of hyperplane will be changed. Okay, so this leads to overfitting. Okay, it leads to the overfitting. It leads to overfitting the training data. So what do we need? So here we need some kind of classifier here. Okay, so here we need a classifier which won't classify observations perfectly. So we don't want to classify all the observations correctly. We are okay to allow some kind of misclassifications. That's what I'm saying, right? We won't classify observations perfectly. We allow some misclassifications. But why? Because of the two reasons. The first reason is it will have great robustness to individual data points. Okay, and other thing is we need to classify most of the observations. So we can ignore few misclassifications. So what I'm saying is here we need a classifier. We need a kind of classifier Okay, so here we need a kind of classifier which won't exactly classifies the observations perfectly. So what I'm trying to say is we can allow some kind of misclassifications also here. That is, we will let few data points to be placed on the wrong side also. Why? Because then only we can we can have the model which is a great robust, I mean, which is a great which has a great resistance to the individual data points. For example, if I change any kind of then only what happens is, uh, see here, then only if I change any kind of individual data points from this location to this location, then it doesn't impact my uh, hyperplane here. So due to that reason, I have decided to build a classifier which is actually classifying most of the observations correctly, but it's also actually allowing some data points to be placed on the wrong side also. Why? Because we have two reasons. It will create some kind of great robustness to our individual data points. That means these individual data points will not impact our hyperplane anymore. Okay, and now we need to classify most of the observations, right? So for example, let's say we have the 100 people. Okay, we have the 100 people. Now our target is to save um, how many number is possible. I mean, our target is to save most number of people, right? For example, our target is to save most number of people. That is no worries. I mean, for example, we have the 90. For example, we have the 90 people here in this particular building. Okay, and here we have some 10 people, and we here we have 10 people inside a building. So we are actually located here. Okay, we are actually located here. So the distance to this building is very short, but if we want to reach this particular building, we need to travel so far. So what do we do? For the sake of this just 10 people, you will sacrifice these 90 people's life? No, right? Why? Because here we can reach to this building very quickly, and here we have the maximum number of lives, right? Here we have the maximum number of lives. So in order to save these 90 people, what I can do is I can just first approach this building and save them. And if I have any kind of further time, then I can still approach this particular building and save those 10 people's lives also. But instead of saving these 90 people's, I can't even approach this building and save those 10 people's by sacrificing these 90 people's life, right? So first of all, I mean, for me, the number is important here. 90 lives are important instead of these just 10 lives. Of course, every life is very important to everybody. But here, what I'm saying is the perspective here. Our perspective should be should be towards the greater side, right? We need to protect these 90 peoples mainly, and if we have the time, later we can protect these 10 people. So that's what it did, right? We need to classify most of the observations as for, I mean, as much as possible, right? But we can still ignore few misclassifications, because if we try to eliminate these few misclassifications, then our whole observations will get impacted. So we should not do like that. We can allow few misclassifications by allowing most of the data points to be classified inside a correct side of the hyperplane, right? I'll explain this with the help of an example, don't worry. I'll explain that, but before that, just you need to understand one thing, like what is mean by the SVC. SVC has another name, that is nothing but the soft, soft margin, soft margin classifier. Okay, SVC. SVC is nothing but support vector classifier. Support vector classifier. We can also call this particular support vector classifier as soft margin classifier. So why we are actually using this soft margin, I'll explain that in the coming example. Okay. So I'll explain that. Uh, let's say we have our feature space like this. Okay, we have the feature space like this. So we have a kind of hyperplane like this. Okay, we have a kind of hyperplane like this, and we have the data points here like 1, 2, 3, 4, and 5. Okay, and we have another data points here like 6, 7, 8, 9, 10. Okay, so what happens is here we have the let's say here we have the let's say here we have the margin. Okay, let's say here we have the margin here like this, and here also we have the margin here like this. So what happens here? So meaning of this particular plot is most of the data points are actually on the correct side. See here, this will be the critical hyperplane. I mean, this will be the actual hyperplane. So everything that lies right off to this hyperplane is nothing but it will comes under one category. Okay, it will comes under one category. Everything that lies left to this hyperplane is nothing but everything that comes under one category. These categories belongs to the green. This categories belongs to the blue, right? So that's what it is. And but yes, only some you see here this particular 4 and the 5 and 3 which are actually on the wrong side. Why? Because why I'm saying this particular word wrong side? Why? Because it's actually crossing this margin. Okay, we are actually allowing it to cross this particular margin. Here also it's the same scenario. Here also this particular 6, 7 and 10 are actually crossing the margin. Why? Because we are actually allowing, our classifier is actually allowing them to cross this particular margin here. So so here most of the, let's say most of the data points, okay, for example, I haven't provided some most of the data points here like 11, 12, 14, 13, 15, 16, you can call whatever it is. Okay, and here the scenario is uh, let's say 20, 21, 32, 35, whatever it is. Okay, so here by the end of the scenario we can conclude that most of the, see here, these are the most people, right? These are the most of the data points are actually on the right side. Okay, they didn't cross this particular margin. Okay, but very few of the data points are actually crossing the margin, and we are okay to, and we are also okay with that. We are actually allowing these data points to cross the margin. Why? Because see here we are actually saying soft margin. Soft is nothing but we are actually showing some kind of soft corner. We are actually showing some kind of mercy on them, right? No worries, you can cross our border. We are actually allowing them to cross our margin. So that's why this classifier is actually doing most of the data points are actually on the correct side of the hyperplane, correct side of the margin, but very few data points are actually on the wrong side of the margin. Here also the same scenario. Most data points are actually on the correct side of the margin. Okay, these data points are actually on the correct side of the margin. Why? Because they didn't even cross this margin. But these data points are actually the bad data points which have crossed. But no worries, we are actually okay with this. Why? Because our classifier is actually allowing these data points to cross this particular margin. So the entire conclusion for this classifier is nothing but most data points are lying on correct side of margin. Only few data points are on the wrong side, of the margin. Okay, so this would be the conclusion for this particular example. Now I'll show you another example. Looks like our jam book has been filled. So what can we do? Just go to this and we can create another jam book. So I'll explain here. I'll explain another example here. See here, for example, we have this kind of dimensional space, feature space. Okay, and we have, let's say we have a hyperplane here. Okay, and these are the margins here. What happens is I have few data points. Okay, actually, one, two, three, 4, 5, 6, 7, 8, 9. Okay, and we have here, we have 10, 11, 12, 13, 14, 15, 16. Here we have 17, we have 18, the 19. So what is the conclusion for this example? So here also this very similar to the previous example, right? Why? Because see, everything that lies under the margin are the data points which are actually lying on the correct side of the hyperplane. Okay, so these data points are actually lying on the correct side of the hyperplane. Why? Because these are actually under the margin, right? These are actually under the margin or away from the margin. Okay, but here when you look at here, these are the three data points. This data point, this, and this data point is actually lying on the margin. This is a bad, and this one is also below the margin, that is within the margin. So this, which is a bad, this is also within the margin, this is a bad. So those three, right? So those three data points are on the wrong side. Okay, the same with the here also the same with this case. Every data point which is actually lying far from the margin are actually on the correct side. Okay, but these data points which are actually within the margin, these are on the wrong side. Okay, so our goal is to, if we have this particular hyperplane like this, and we have some kind of margins like this. So our data need to be present here, away from the margin here, and it should be present here, away from the margin here. Okay. For example, if any data is placed here or here within the margin or on the margin, then this particular data points are actually on the wrong side of the margin, and we are okay with that, right? Why? Because we are actually support vector classifier. Support vector classifier. This, what does this support vector classifier do? This support vector classifier will actually do uh, it just allows some of the misclassifications. Okay, it just allows some data points. Okay, it's okay for me to cross this particular margin. Okay, no matter, no worries. There is absolutely no problem. I don't have any kind of problem if you cross this particular margin. It will say like this. Okay, so this is the particular support vector classifier, which is nothing but a more generalized form of the maximal margin hyperplane or maximal margin classifier. Okay. See here, you should observe one thing. If I say a particular data point is actually on the wrong side of the margin, then it also means it is also lying on the wrong side of the hyperplane, right? Got it? If it is lying on the wrong side of the margin, then it also means that this particular data point is actually on the wrong side of the hyperplane also. Okay, you should keep this in mind. But one thing, when do we get these kind of situations? When do we get these kind of situations means we will get these kind of situations when we don't have any separating hyperplane naturally. Okay, naturally in the sense, for example, we have some kind of data like this. We have some kind of data like this, and here, between these two categories, we have a natural gap which is acting as a natural classifier, right? If we don't have this kind of gap, for example, we have the data point like this. Okay, and again we have the data point like this. See here, yeah, do we have any kind of gap here, the natural gap? No, because the data points are actually looking like very close to each other. So here we can't even say that, we can't even separate like this, right? So in such cases we occur this kind of scenarios, that this data point is actually on the wrong side of the hyperplane, and this point is actually on the wrong side of the hyperplane. This situation arises when we don't have the natural separating hyperplane, like in the maximal margin classifier scenario. Okay, if we don't have this natural gap here like this, we will get this particular situation where our data points will be misplaced or wrongly placed on the hyperplane, right? So I have already explained what is meant by SVC classifier. Now I want to explain how does the SVC. I'll explain here. How does support vector classifier classify an observation? See, I'm giving the solution here. The support vector classifier, it will actually classify any data point based on the side of the hyperplane. For example, here we have the hyperplane. here we have the margin. So based on the which side, if I have a data point like this here, if it is present here, that is away from the margin, then it will usually belongs to this particular class. If our data point is actually away from the margin here, then this data point is actually belong to this particular class. So with the help of this kind of approach, we can classify any data point in this kind of approach, right? So similarly, support vector classifier also classifies any observation based on this kind of approach. But here what happens is this SVC, that is these support vector classifiers, will allow most of, will actually classify most of the data points correctly. That is, most of the data points will usually present the far from the margin only. But very few data points will actually present inside this margin, that is within the margin. That means it will actually allowing few data points to misplaced, right? So that's the property of this particular support vector classifier. So I'll explain this mathematically now. By this you can get some kind of understanding. So here this is very much similar to the maximal margin pair. Why? Because SVC is nothing but a generalized form of the maximal margin hyperplane, right? So that's all. So earlier we have seen some kind of optimization problem, right? Optimization problem. So this is the solution of that particular optimization problem. So what is that optimization problem? See, we have already seen that maximize, right? We need to maximize capital M. Here we have the parameters beta 1, beta, and so on, beta p. These are the parameters here, and this implies j equal to 1 to n beta j whole square is equal to 1, and yi of beta naught plus beta 1 plus and so on, beta 1 x1 plus and so on plus beta p xp, it should be greater than or equal to capital M, right? So this would be the scenario. If we calculate this entire expression, and if that expression is greater than capital N, then we can say that each data point is actually placed on the correct side of the hyperplane, and also with the distance m, right? We can say that. So this is the optimization problem, and the solution for this particular problem is this one. Okay, the solution for this particular problem is, now I'm going to explain this. See here, we have epsilon I is equal to greater than or equal to 0. We have epsilon I greater than or equal to 0. That is sigma I equal to 1 to n epsilon I less than or equal to c. See here, epsilon should be greater than 0, and it should be less than c. What is this c here? C is nothing but the tuning parameter here. Tuning parameter. And what is this particular m here? M is nothing but the width of the margin, right? Width of the margin. So clear up to now? So I'll explain what is this mean by this epsilon and what is this c or the tuning parameter. I'll explain all those things. Just wait a minute. Just remember this. Epsilon should be greater than or equal to 0, and it should be less than or equal to c. I'll explain why it should be the condition. Okay. So our goal is to maximize m as large as possible. So that's nothing but in yi beta naught plus and beta 1 x1 plus and so on plus beta p xp, if it is greater than 1, if it's greater than m of 1 minus epsilon I, then so in this equation, so see here, this equation would be like this. It should be greater than m of 1 minus ei. Okay, so here I'll explain each of those notations. Epsilon 1 comma and so on comma epsilon n are nothing but the slack variables. These are the slack variables. Okay, what is mean by these slack variables? What do they do? These allow our data points to be on the wrong side of the margin. Wrong side of margin or hyperplane. See here, earlier I have already said, like few, see, earlier I have said like there are some kind of data points which are actually within this margin. That is, these data points are actually misclassified. These are placed inside this margin wrongly. These are actually placed on the wrong side of the hyperplane, right? So who are actually allowing these data points to cross this particular margin? That's those, nothing but this epsilon. Epsilon is actually allowing. What is mean by this epsilon values? These are the slack variables. These are responsible for allowing our data points to be placed on the wrong side of the margin or the hyperplane. Did you get my point? Did you get my point? So that those slack variables are actually allowing our data points to be placed on the wrong side of the margin. See, the rule is the data points should not be placed within this margin. There should be somewhat gap between the data points and the margin here. But these are actually placed on the wrong side, that is within the margin. And who are allowing them? These slack variables are actually allowing them to be placed on the wrong side of the margin, right? And see here, the value of this slack variable, it should be greater than 0 and it should be less than or equal to c. C is nothing but the tuning parameter, and I'll explain what is meant by this tuning parameter. So here also, as of the maximal margin, just like the maximal margin plane, here also we classify data point based on the sign of the function. That is, we calculate the f of x is equal to beta naught beta 1 x1 plus and so on plus beta p xp. We calculate this if epsilon is equal to, and see here, if I'll explain, if f of x value is greater than 0, we classify a data point that is belong to so and so class. Let's say it belong to apple class. Okay, if f of x is less than 0, that is, if it is negative, then we can say x belong to, let's say, banana. See, we can actually say that it belongs to banana, right? So based on the sign of this function, we here also in the support vector classifier also, we follow the same procedure as of the maximal margin classifier. Okay, here also we usually depends upon this sign of this f of x. Here also we usually depends upon this sign of this f of x. And additionally, we also look for this particular value of the slack variable, that is epsilon I. if epsilon I is equal to 0, if its value is 0, then what does that mean? Then our data point is actually on the correct side. Our data point is actually on the correct side of the margin, right? If epsilon I is less than 0, then what happens? This data point is on the wrong side of the margin. Okay. And if epsilon I is greater than 0, what happens? This data point is on wrong side. Okay. Here also it's on the wrong side, but not wrong side of the margin, but wrong side of the hyperplane itself, right? It's actually crossing the hyperplane. See the difference here. If epsilon I, that is this, if the value of the slack variable is 0, then we can confidently say that it is present on the wrong side of the correct side of the margin. If the epsilon slack variable is value is less than 0, then we can say that data point is actually on the wrong side of the margin. See here, in the both the cases, the data points are actually on the sides of the margins itself. See here, the margins. Just note this word. And here, if epsilon I is greater than 1, we can say data point is actually on the wrong side of the hyperplane, not the margin, but the hyperplane itself. Got it? Now I'll talk about what is meant by a tuning parameter, that is C. So you will get the clarity. So I'll talk about the parameter here, tuning parameter. So we everybody know that SVC can allow misclassifications, right? SVC can allow misclassifications, but do you know up to how much number? But up to how much? But up to how much level does SVC allow misclassifications? So up to what number does our SVC, that is support vector classifications, allow misclassifications? Do you know that? So this will be find out by tuning parameter C. C can find out up to what number we can allow misclassification. Did you get that? Okay. So that's nothing but, for example, if the C value is 0, then we can say epsilon I is equal to 0. If C is 0, then epsilon I will also be 0. Then every data point should be correctly classified. Got it? Should be correctly classified. That means if C is equal to 0, then there is no chance of allowing misclassifications. Okay, then we can't even allow misclassifications to happen. Got it? For example, if our C value is greater than 0, then what happens? That is, EI value will be greater than 1. That is, EI value will be greater than 1. And this needs EI should be less than or equal to C also. Okay, EI value should be less than or equal to C, and it should be greater than 1, but C also greater than 0. Okay, so then what happens? Then not more than the value of C, we allow data points to be on wrong side of the hyperplane. So what does this mean? If our C value is greater than 0, that means E value should be greater than 1, right? This requires C value should be, epsilon value should be less than or equal to C. Okay, it needs the condition. If C is greater than 0, then the data points should satisfy. The slack variables should be greater than 1, and our slack variable should be less than this tuning parameter C. Then only we can say whatever may be the value of the C is, up to that level we can allow the misclassifications. But beyond that level, we can't even allow our data point to be placed on the wrong side of the hyperplane, right? For example, if the C value is 20, okay, we can allow misclassifications up to 20 data points, but the 21st data point should be placed on the correct side of the hyperplane only. It should not be allowed on the wrong side of the hyperplane. Okay, only 20 data points should be allowed. This is an example. Okay, this is an example. If the C value is 20, then we can allow those 20 data points to be placed on the wrong variables, but it should not cross that particular value 20. That's what it is. Okay. Now what happens is, if C increases, okay, if C increases, then more misclassifications are allowed. This implies our margin will be widened. Okay, our margin will be widened. Then what happens? If the margin will be widened means, then what happens? Then it should have the high bias and low variance. Okay. And what if the C is decreases? If C is actually decreases, then what happens? Only few misclassifications are allowed. That means margins will be very thin. Okay, margins will be very thin, or we can call margins will be very small. Okay, and then it has low bias, high variance. I'll explain what happens if we have this high bias, low variance, and what happens if we have low bias, high variance. I'll explain them. But just remember this in mind, and also take a screenshot of this, or no worries, because in the end of the video, I'll be sharing all these Jamboard file. I mean, inside the description. So don't worry. Just concentrate on the content here, right? If you understand this concept, then you can definitely answer any questions that belong to support vector machine, right? See here, if C this tuning parameter is increasing, then more classifications are allowed. Then what does that mean? Then I'm saying I am actually widening my margin so that there may be possibility of many data points to be placed on the wrong side of the margin. So no worries. I can tolerate more data points to be placed on the wrong side of the margin. So no worries. You can send all the data points to this particular within the margin. I have more wider margins. So I'm saying like this. Okay. If I am saying C is decreasing, then I have only the shorter margins like this, right? That means only few data points I can tolerate. More than few data points I can't tolerate because my margins are very small, right? And in this scenario, we have high bias, low variance. And in this scenario, we have low bias, high variance. I'll explain what does this concept means at the end of the video. Okay, I'm just moving to the next slide. So when do we choose the C? When do we choose tuning parameter C? Nothing but we choose C in cross validation. In cross validation, we will use this particular tuning parameter. See the word tuning parameter, right? Tuning means we need to improve by changing this particular tuning parameter. We will get we will get slightly improvised version of our model, right? So this is nothing but the tuning parameter. The name itself it defines. It will be used inside this cross validation technique, which is very helpful in increasing the efficiency of the model, right? So what happens? This C, this tuning parameter C controls bias, variance, and trade-off. Bias, variance, trade-off. It can be controlled, right? It can be controlled by this particular tuning parameter C. How do we do that? What does this actually bias, variance, trade-off? I'll explain at the end of the video. Just because that will be another slightly diverting concept. So if I start that particular concept of bias, variance, trade-off, then it will be, I think I'll get diverted. So I'm not explaining right now, but at the end of the video I'll definitely explain. Okay, so here C will be used in the cross validation technique, and C usually controls the bias, variance, trade-off. Okay, and now here the support vector classifier, the SVC, is impacted. Not is impacted, but is also impacted only by the support vectors, right? Support vectors. What is meant by the support vector? If we have the hyperplane like this, and we have the margin like this, and on exactly on the margin, we found some kind of data points, right? We found some kind of data points. These data points which are lying exactly on the margin are nothing but the support vectors. So here we are saying if we change any data point, any of these data points, then only it will impact our support vector classifier, which is this straight line. Okay, then only our support vector classifier will get impacted. If I change the rest of the data points here outside of the margins, then it won't have any impact on this particular support vector classifier. Clear? That's it. and I'll explain with the help of an example what happens when C is increased and what happens when C is decreased. Okay, I'll explain them. After explaining them, I'll end the session. Why? Because it's already a bit lengthy. So I want to end this session as soon as possible. So I'll just explain the example here. For example, if I have the situation like this, it has a it has my three-dimensional space here, and here, let's say I have some kind of data points here. Okay, I have some kind of data points here. I have the data points here. Okay. This is our classifier. Okay, this is our classifier, and this will be the margin. Okay, this will be the margin. So this will be the case when our C is large. C is large means we are actually allowing more data points to be on the wrong side of the hyperplane. That is, we are actually allowing all our data points to be placed on the wrong side. That means for that, if I want to allow all the data points to be placed on within the margin, I need some kind of wider margins. So here, let's see, here see, the gap between the margin and the hyperplane is actually very large, right? This happens when C is large. Okay, and I have another scenario like this where have the hyperplane here, and this is my margin, this is my margin, and there lies so many data points here, there lies so many data points here, so many data points. Okay, this situation occurs when C is of small. If our C is small, that is tuning parameter is small, then this kind of situation occurs where the gap between the margin and the hyperplane is actually very, very small. Okay, so, and we also have some kind of situations here. Yeah, so that's a kind of the almost similar, right? So if C is large, the gap between the hyperplane and the margin will be maximum, and if C is small, the gap between the hyperplane and the margin is very, very small. That's the conclusion for it. Okay, and what is the difference between the what is the difference between the LDA classifier, linear discriminant analysis, which is usually used to classify a data point, whether it is belongs to +1 category or it belongs to -1 category, similar, just like the SVM. But what is the difference here? Actually, LDA depends on mean of the data points, right? It needs the mean of the data points. It calculates the mean of all the data points, right? And also it calculates the covariance matrix of the data points, using all the data points and so on, right? LDA calculates the mean of all the data points, and also it calculates the covariance of all the data points. But here, logistic regression, when I say the logistic regression is also used for the classification, right? So when I say logistic regression, what happens is it has very sensitive to the data points that are far from the decision boundary. That's nothing but a logistic regression won't consider the data points which is actually. I'll explain this in this particular. For example, I have some kind of data points like this, and I have some kind of data points like this. Okay, so this is a sigmoid function, right? Everybody knows that this is a sigmoid function. For example, there are some kind of data points which are lying on the wrong side of the decision boundary. This is nothing but a decision boundary, sigmoid. And here we have some kind of data points which are actually lying on the wrong side of the data point, right? So it won't, it will consider, but see here, if these data points are actually far from this decision boundary, it won't be considered. For example, I have the data points here somewhere, right? It won't be considering. Logistic regression won't consider these data points. It will only consider within the range of these particular data points, right? This is the range. So if the data points are actually in the range, then only logistic regression will consider this or that. For example, if this is particular, let's say here, somewhere here, okay, then it won't be considering these data points. Just like the just like the support vector classifier also. Why I'm comparing this logistic regression with the support vector classifier? Why? Because see here, we are also not worrying about these particular data points which are actually lying far from the margin. We only consider the data points which are lying inside this particular margin, right? We only consider for these data points inside this margin or on exactly lying on the margin, but we don't bother about these data points which are actually far from the hyperplane or the margin, right? So by this we came to end on the topic of support vector classifiers. So far we have how many topics I have covered? Let's have a look. See here. See here. First of all, I have covered what is meant by the maximal margin hyperplane with the help of the definition, and also have given mathematical expressions with the help of mathematical expressions I have already explained, and and also explained with the help of so many diagrams. Okay, and then I used to explain what are meant by these support vectors. Support vectors are nothing but we have a hyperplane like this, and we have the margins like this, and there are so many data points which are actually lying on the data points, actually lying on the margin. Okay, what are these data points? These data points are actually wrongly placed. Why? Because every data point should be ideally away from the data, away from the margin, right? This is the ideal way of placing the data points. But if I find any data points that are actually placed on the margin, then we can call these data points as the wrongly placed, right? These wrongly placed data points are nothing but our support vectors. These data points will actually support this particular classifier or the hyperplane. Okay, so I have explained what is meant by maximal margin classifier, and then what are all the limitations. Limitations for the maximal margin classifier is nothing but the non-linear case. That's nothing but if we have all the data points separately, we can use maximal margin hyperplane like this. But what if all the data? But what if all the? But what if all the data points are actually mixing? Okay, all the data points are actually both the classes are actually mixing like this. mixing like this, then we can't even apply this maximal margin classifier to this particular data. Why? Because it is sensitive to this non-linear scenarios. It is only applicable for the linear scenarios. So that would be the limitation of this maximal margin classifier. So I have already explained what is meant by support vector classifier, which is nothing but the more generalized form of this maximal margin classifier. Okay, I have explained what does how to build a support vector classifier with the help of the equations also, and I have given so many scenarios. Nothing but the how to control the how to control these particular data points that are to be placed on the wrong side of the hyperplane, which is controlled by the tuning parameter C. I have explained about this particular C, and I have explained about the slack variables E, epsilon I, and have given so many conditions. What should be the value of the C and what should be the value of the epsilon, and what happens when C is large, what happens when C is small. I have given all those scenarios, and we have only left with two topics: support vector machines and applications, which are of the which I will be explaining the rest of the two topics in the next video. So this is the end of this video. So I'll see you in the next video. So just take some kind of screenshots, or just no worries, I can share the entire file in my description. So by just constantly or focusedly, if you can watch the entire video, then you'll definitely able to understand what I'm trying to say. And after that, you can go to these particular slides. By that, you can easily understand what I'm trying to say or what I have tried. See here, by going all these slides, you can definitely understand, right? So these I have explained some 20 slides here. Okay, by this you can definitely develop some kind of understanding about the SVM. Here I have explained the entire support vector classifier or the support vector machines concept one by one inside this particular series. So I'll be explaining all the remaining other algorithms also. So just be patient and subscribe to my channel. And if you like my intuition, or if you like my way of teaching, then just share all the videos with your friends so that it can reach to the maximum number, right? So okay, that's all for this session. I'll see you in the next video. Good night, take care, Jai Hind.